Today I'm gonna show you the understanding the asymmetrical thermoelectric performance for discovering promising thermoelectric materials. And it's talking about the thermoelectric modules consisting of multiple pairs of N and P-type legs, enable converting heat into electricity and vice versa. However, the thermoelectric performance is often asymmetrical, in that one type outperforms the other. In this paper, we identify the relationship between the asymmetrical thermoelectric performance and the weight mobility ratio, a correlation that can help predict the thermoelectric performance of unreported materials. Here, a reasonable high ZT for the N-type base heuristic is first predicted and then experimentally verified. A high peak ZT of about 1 at 973 K can be realized by cobalt and nickel doping. The measured heat to electric conversion efficiency for the unit couple of base materials can be as high as 10% at the cold side temperature of around 3.3 Kelvin and the hot side temperature of around 983 Kelvin. Our work demonstrate that the base heuristic are highly promising for the application of mid and high temperature thermoelectric power generations. Solid state, and the introduction is talking about the solid state energy conversion from heat to electricity and vice versa can be realized by a thermoelectric module using a thermoelectric material. The conversion efficiency of the module is governed by the Carnot efficiency and by the material's figure of merit. ZT equals to the S squared sigma over kappa, where which stands for Seebeck coefficient, electrical conductivity, lattice thermal conductivity, electronic thermal conductivity, and absolute temperature, respectively. Generally, the thermoelectric module consists of multiple pairs of N and P-type legs that are connected thermally in parallel and thermoelectrical in series. To achieve a high energy conversion efficiency, high thermoelectric performance for both types of legs is desired. In addition, to minimize the thermal stress that originates from the mismatch of the thermal expansion coefficients between N and P-type legs, it is preferable to adopt the same base compound for both types of legs. However, there are quite a few materials that can only by synchronous as a one of type, like magnesium and tungsten and GETE and DMSB. This can be attributed to the presence of native defect that pin the thermal level to either the conduction or the valence band, and therefore the material shows presented N or P-type conduction. Among the materials for which the and bipolar doping can be realized, most show high thermoelectric performance. For example, ZT is bigger than 1 is only one of the types. For example, magnesium tin based or magnesium Sb based or zinc nickel tin based, and so on. Even for the state-of-the-art thermoelectric materials, bismuth tolerant-based materials, lead chalcogens, sculpturals, and silicon germanium, in which high thermoelectric performance can be achieved in both types. The thermoelectric performance is often asymmetrical. The specific reason for such an asymmetric varies around the different compounds. It could be attributed to the difference in the electronic structure between the conduction and valence state. For example, density of state, effective mass, inertial effective mass, and the band degeneracy. It can also be ascribed to the difference in the carrier mobility due to the different degree of carrier scattering. In addition, disparity in the dopability, for example, difficulty in identifying an efficient dopant for one of the types can also lead to asymmetrical thermoelectric performance. Asymmetrical thermoelectric performance for previous reported materials has been merely viewed as an observation, while a more general relationship between the asymmetry and the intrinsic material parameter is seldom discussed. Therefore, it would be highly meaningful to quantify the asymmetrical thermoelectric performance and identify the relationship between the symmetry and the material's parameters. This would be highly beneficial for understanding the asymmetrical thermoelectric performance. Once the relationship can be identified, it will be possible to predict the thermoelectric performance of an unreported type of given material by using the material's intrinsic parameters. Such a strategy could possibly be helpful for identifying promising thermoelectric materials. And for the result part, asymmetrical thermoelectric performance and materials parameters. For the first part, generally the latest thermal conductivity of optimized negative and positive type compositions of a given material system are similar. Therefore, we mainly focus on the electronic transport properties of the materials. The electronic contribution to the thermoelectric performance are given by a power factor, which can be optimized by chemical doping. The thermoelectric performance of a given compound can be estimated by the dimensionless material quality factor B. And B is an equation that about the mobility and the effective mass and the kappa. This formula captures the essential aspect that heavy effective mass, high carrier mobility, which typically accompanies light mass and it is needed for conductivity, and low lattice thermal conductivity are all needed for thermoelectric performance. When asymmetrical thermoelectric performance is observed for the certain compound, this asymmetry can be estimated by the below formula. where N denotes the negative type and P denotes the positive type, and kappa L and the temperature for peak ZT are considered similar for both negative or positive pies of the compound. A is the dimensionless negative type to positive type weighted mobility ratios. The density of state effective mass is related to the band effective mass by the relationship of the degeneracy and the band effective mass. In addition, in the case when carriers are mainly scattered by acoustic phonons, the carrier's mobility depends on the band effective mass as well as the inertial effective mass according to the relationship of mobility equal to the inertial effective mass and the band effective mass. For an isotropic single parabolic band systems, these masses are identical, and in general case, they are decoupled and are also dependent on doping and temperature. Equation 2 can thus be rewritten as the following equations. It can be understood from equation 3 that the large band degeneracy and the low inertial effective mass can be greatly beneficial for high thermoelectric performance. As a result, the difference in the band degeneracy and inertial effective mass between the conduction and valence band will lead to a noticeable asymmetry thermoelectric performance. According to equation 2, the asymmetrical thermoelectric performance can be estimated by the weighted mobility ratio. The weighted mobility ratio for different materials could, in principle, be calculated by equation 2. For estimation of A, this can be done at similar electron and hole carrier concentrations. The relationship between negative and positive type ZT ratio, and then the negative to positive weighted mobility ratio is shown in figure 2a. There is general trend that ratio increase with the weighted mobility ratio. For example, details of this data used in this fitting can be found in table S1. It should be noted that experimentally obtained relationship between log and log A is in a reasonable good agreement with the theoretical calculations. You can see the section S1 and figure S1. Specifically, when the weighted mobility ratio is larger than unity, the negative type materials will outperform the positive type counterpart. Conversely, when the weighted mobility ratio is similar than unity, the positive compound will demonstrate better thermoelectric performance. When the thermoelectric performance for one type of materials has been experimentally studied, while the other type has not yet been investigated, it is possible to predict the ZT by using the identified relationship between the asymmetry and weighted mobility ratios. In this case, because the carrier mobility for the unreported type can be obtained, equation 3 can be adopted to estimate and weighted mobility ratio. Thus, it only involves the material's basic parameters that can be determined by calculations. However, it will be noted that equation 3 is simplified by assuming that the carrier scattering is similar for electrons and holes. Therefore, the estimated weighted mobility ratio by equation 3 could be different from the value experimentally determined by equation 2. Here we have predict the thermoelectric performance for several materials as shown in figure 2b. Our prediction indicate that the reasonable high ZT can possibly be achieved in negative type titanium and negative type of GETE and N type of ZrCoBi. In addition, a negative type of TAFE-ASB and positive type of NBCOSN are possible candidates for very promising thermoelectric performance. However, SNT and GT has been proven as very persistent positive type materials, so we limited our investigation to the thermoelectric properties of Houston materials. Currently, we have not yet identified efficient dopant for positive type of NBCOSN or negative type of TAFE-SB. Therefore, we mainly discuss the thermoelectric performance of N-type ZrCo-based material in this book. The electronic structures of ZrCoBi. The thermoelectric theoretical calculations of the electronic structures of ZrCoBi were first conducted to provide preliminary insight into the thermoelectric performance. The calculated band structures of ZrCoBi is shown in figure 3a. The valence band shows practically degenerate maximum at sigma and L, which is previously discussed. Band degeneracy, band convergence. It should be noted that there are strong splitting in the band as one moves away from sigma. These are the splitting into the heavy and light hole band along the sigma to X path, and addition splitting of upper heavy hole band below sigma to L. This later splitting would be forbidden without the combination of spin orbit or and non-centrosymmetry. These effects are strong due to the large differences between cobalt and Zr and the heavy p electron element bismuth, which leads to strong breaking parity symmetry. Although sigma has the full cubic symmetry and the inverse effective mass tensor of a cubic material is isotropic, and bands at sigma are eventually high and isotropic. This anisotropic with different curvatures in different bands and directions at sigma provides a mechanism for decoupling the electric conductivity and the Seebeck coefficient, in particular with the high curvature areas, leading to a high electrical conductivity. Even more notably, at other peak at pocket L, there is a pair of twofold degenerate bands separated by around 0.6 eV. Both are relevant for the thermoelectric transfer due to this small splitting. The upper band is seen to be very strong spin split from L to W, and somehow were weakly sold on L to sigma. The splitting would be forbidden by the combination of parity and time reversal in the central symmetry case. This is important because in addition to an isotropic load in a parabolic system around the L points, for example, the transverse and the longitudinous maze, which can be different as in germanium, there is an additional separation into a light and heavy band due to spin orbit. This is highly favorable as it again decouples feedback coefficient and electrical conductivity. In constraint, the conduction band is apparently simpler, although it also shows different strong influence of spin orbital. This band shows a sustainable spin split along X to W path, but not X to sigma. This stress causes spin split shift the conduction band minimum away from X perpendicular to the X to sigma line, and can be also decouple the feedback coefficient and the electrical conductivity. Although the decoupling is less pronounced than is the valence band. Visualizations of the carrier pocket of 0.1 eV from the band edge for the positive and negative are shown in figure 3. The band degeneracy is 10 for the p-type, but only 3 for its n-type counterpart. In addition, the calculated inertial effective mass is shown as a function of carrier concentrations for positive type and n-type DCB in figure 3b. It should be noted that the inertial effective mass is smaller. It's very smaller for positive type and n-type DCB. As a result, the value of is around 3.3 for p-type and only 2.0 for n-type counterpart, which corresponded to the n-type to p-type weighted mobility ratio of around 0.42. By using the experimentally determined the thermoelectric performance of p-type and the weighted mobility ratio of 0.42, the predicted DT for the n-type of DCB is about 0.71. That is, despite the symmetrical thermoelectric performance of DCB, reasonably high thermoelectric performance could possibly be achieved in the n-type DCB.